the discrete time martingale. That means I have a sequence xn which is adapted to the filtration fn, and it is integrable for every n, and expectation over x of n plus 1 given fn, if it is equal to xn, then we say that it is a martingale. Okay, and then we have seen some examples of martingale and so on, and then we are discussing towards the convergence of a martingale. Okay, when one's because it is a sequence, is it not, for each or for almost every omega, you can think of the path, so it is a sequence, and for there we know, like in real number sequence, no, the intuitively we know that, okay, if you look at the upcrossing, so if the number of upcrossing, if it is finite, or number of downcrossing, if it is finite, then the sequence will converge, otherwise it will not converge. Okay, this idea we try to use here. Okay, so for that, what we have proved, the upcrossing inequality, what it says that, so suppose you have a non-negative submartingale xn, and then you look at un. What is the un? Un is nothing but the number of upcrossing up to time n throughout the interval a b. Okay, for a greater than a is less than b. And then what we have seen, that we have seen that b minus a times expectation of u of n, because un is a random variable, this one is less than or equal to what we have, that is expectation of xn minus a plus minus expectation of x0 minus a plus, isn't it? So that x plus means basically this is maximum of 0 and x. Okay, so we try to use this upcrossing inequality to prove the convergence of a martingale. In particular, under what condition we can say that given say martingale or submartingale, it has a limit as n goes to infinity, and then we'll talk about whether this limit exists almost surely, or maybe we can say more, means whether it converges in L1 or not. Okay, so for that, as I told you, just looking at this upcrossing inequality, so under this condition, so maybe I put as a theorem, that is called the martingale convergence theorem. What it says that, so suppose my xn, this is a submartingale, okay, such that supreme over n expectation of xn plus, this one is finite, it is given to you. Okay, xn plus, we don't know whether xn is a non-negative martingale or not. If it is a non-negative, okay, a submartingale, then basically xn plus is same as your xn, or I can think of a mod of xn. Okay, that should be finite, but it is given to you. So then what I try to show is the following. Then there exists a random variable x such that my xn, this converges to x almost surely as n goes to infinity, and we can expect, so this is a submartingale, then this part is there, so we can expect that expectation of x, okay, or mod x, it should be finite. This is actually we can expect that expectation of mod x is finite. So what are the conditions now? This theorem says that if you have a submartingale such that supreme over n over expectation of xn plus is finite, then there exists a random variable x such that xn converges to x almost surely. Is it not? So what that means, basically you look at that that all those omega where limit xn goes to infinity xn does not exist or not equal to x, and look at that omega, take the probability, that gives you 0. Okay, that is the almost already you have seen it in your previous course, in probability course, that what is the notion of xn converges to x almost surely. Let us try to do the proof, and as I said, that proof based on our approaching inequality. So in the approaching inequality, what I have, so now look at x minus a plus, this is always less than equal to my x plus mod of a, is it not? So using these things, what I can write down from the approximate lemma, approximate inequality, what we have the following, that expectation of un, as I said, that what is your un? Un is the number of approaching by the sequence up to time n throughout the interval a b. So this is less than or equal to, I can write mod a plus expectation over xn plus divided by b minus a, because that is less than equal to minus expectation of x minus a, so that is negative term, so we can omit that part, is it not? This part I have. So now see what is my u of n. You see that if you look, say un plus 1, un plus 2, all these things, so this is increasing, no? Un is increasing. And now suppose I have u infinitive, or you can think of as a u. So what is your u infinitive? This is the number of upcrossing, okay, of AB. This is, I have not write down as a un of AB, but it is there, through the or by the whole sequence. Excel. Okay, so then from here un, this is converges almost surely to my u of infinity, it is also increasing, is it not? Because you see that, okay, if you look at the this is your time grid n, and if you consider n plus 1, then n plus 2, and so on, so it will be increasing number of upcrossings, it will be more, is it not, depending on the paths and so on. Okay, and from here actually what I can see, now u of n, this is converges to converges to u infinity, and expectation of u in this part. Now what do you know, that this is basically finite, this is finite quantity, no, or this part is in L1, I can think of. Hence by Norton convergence theorem, I can say that expectation of u infinity, this is finite. Also observe that since this is the number of approaching, so u infinity, this is greater than or equal to 0 almost everywhere, is it not? So this is a non-negative random variable, and expectation of u infinity is finite. So from there what I can say, that u infinity is finite almost surely. Okay, so in particular, if I look at this omega is in omega, such that my u infinity of omega is equal to infinity, this set is basically probability is 0, is it not? That is the meaning that u infinity is finite. Okay, so now I denote one set, okay, the gamma or the lambda. What is this? This is basically set of all those omega. Okay, this is set of omega such that my x1 omega does not converge to a limit in, say, minus infinity to plus infinity. This is the set I am defining. Okay, so then this lambda, if I try to show that my probability of lambda is equal to 0, then we are done, is it not? Because that means for almost every omega, I have that xn omega, it converges to some random variable x. So our goal is to show the probability of this lambda is equal to 0. Okay, how to prove this? So the thing is that if I try to look at this tau, if it is a subset of my this set, then we are fine. Okay, let's see. So this gamma I can write down. That means basically this is all those omega such that my limit of xn of omega is strictly less than lim sup of xn of omega. Or I can think of that I can find two numbers. So in particular two rational numbers a and b such that this is less than a less than b and this happen. Okay, and not only that, I have to take all these union a b is in q. Okay, and a is less than b. So because if this is the case, I can find there exists a and b such that this is the case, and ab is any real number, and then actually since ab I have, I can think of the union of this part because the rational number are dense. Okay, there, so I can have this part. So this is actually I am writing down union of ab is in q such that a less than b. I am denoting this is gamma ab, this set. Okay, so now you observe that my gamma AB, okay, this is subset of all those omega such that u of u infinity of omega, this is equal to infinity. Is it not? Because already you know that if this is the case, lim sup AB less than this, that means it is a subset of that part. Okay, otherwise actually it will converge. That is the idea we are using this part, and hence actually since this is the case, and then I have this countable union because it is of rational numbers. What I have, that probability of this set, this is less than equal to summation over a b is in my q, a less than b of p of ab, and since this the probability of this part is 0, so from here actually probability of this one is equal to 0, hence you have 0. So that means what? That means basically, so this implies there exists x, a random variable, okay, such that xn converges to x almost surely. So now we have to show that my xn, this part I have to check it, that x is in L1. Okay, this part I have to check it, and this is easily you can check it by using the Fartu's lemma. Okay, so I can leave it as an exercise. So use Fartu's lemma to check that expectation of mod x, this is finite. Nothing else, because in particular what you can write, that expectation of x plus, if you write down, this is less than equal to lim inf of expectation of xn plus, and that is finite already we know, is it not? Using your given conditions. So x is finite almost surely, x plus is finite almost surely, and then you have to show that okay, x is greater than minus infinity. From there also you can use again the Fartu's lemma, you will get it this point. Okay. So in this theorem, what it says that it converges almost surely. Okay, but it does not guarantee. So maybe I can put as a remark. The mathematical convergence theorem does not guarantee that xn converges to x in L1 of omega. Okay, that means basically that expectation of mod of xn minus x, okay, that converges to 0 as n goes to infinity. It does not converge in L1. So that means we should have some example where this is not the case. Okay, let us consider this example. In particular, you consider say zeta k which is our IID, okay, IID sequence of random variable, such that my probability of zeta k is equal to 0 is half, and probability of zeta k is equal to t, means it takes the value 0 or 2, okay, with probability half. Zeta k are the IID. They are independent, identically distributed. And then I consider my Mn, which is the product of k is less than or equal to n of zeta k. Okay, and my consider the sigma algebra Fn. This is sigma algebra generated by, say, my M1, the natural filtration, okay, of my Mn. So it said that Mn, this is actually martingale, and also it is positive, no, non-negative, greater or equal to 0, because whenever zeta k takes 0, zeta k takes value 0, then it is 0, otherwise it will be basically 2 to the power n, is it not, for all whenever it is with probability 2 to the power 1 by 2 to the power minus n. Mn is a martingale, you can check it. This is basically simple. How to check it? Expectation over Mn plus 1 given f of n. This actually you can write an expectation of what is my Mn. From here I can think of, no, this is nothing but Mn and then zeta over n plus 1 given f of n. Is it not? So now Mn is Fn measurable, so I can take out using the conditional expectation property. So this is my Mn and then expectation over zeta n plus 1 given f of n. Is it not? So now zeta n plus 1, this is independent of Fn. Is it not? So this is same as my Mn times expectation over zeta n plus 1. So now you see, from here actually you can see that expectation over zeta k, this is exactly 1, is it not? Because whenever it takes value 0 or 2 with probability half, this is actually 1. So I have, this is Mn almost surely. That means my Mn, it is a martingale with respect to this natural filtration Fn given in this form. And you observe that supreme over n, expectation of Mn is equal to 1, is it not? So supreme over n, expectation over Mn, this is actually is equal to 1. Okay. And hence actually what I have, because all are zeta k, the expectation of zeta k are 1, and they are the IID independent, hence actually you have this 1. So it satisfies the conditions of martingale convergence theorem. Is it not? Because it is positive, so plus there is no meaning for that. Always it is Mn, it is same. So that means my Mn, this converges to M infinitive. I can just write down the notation almost surely. Is it no? So this M infinitive, then what I can have? This is greater or equal to 0, non-negative. So then actually this is greater than or equal to 0, M infinitive. One can easily check that. Is it not? Because Mn is greater or equal to 0, so M infinitive we will have greater or equal to 0. So now you check yourself, actually M infinitive, basically it is equal to 0, because it can't be positive. Why this is so? Because you see that with probability these things actually it is there, so M infinitive it is actually is equal to 0. So that means my expectation over M infinitive, this is actually is equal to 0. Is it not? So then can M infinitive converge to M infinitive in L1? It is not possible. Is it not? Because what we know that if xn converges to x in L1, then expectation of xn, this should converge to expectation of x, but expectation of xn, or in this case mn, is equal to 1 and expectation of m infinity is equal to 0. So it cannot converge to L1. Okay. So 0 is equal to expectation over m infinity. This is not equal to limit n goes to infinity expectation of mn, which is actually 1. So mn does not converge to m infinity in L1 omega. This is one simple example. What it says that the Martingale convergence theorem only ensures almost sure convergence, not more than that. Okay. So later on, actually, we will see necessary and sufficient conditions. So it should be a uniformly integrable. Then we can have almost sure convergence as well as L1 convergence. Not only that, it is a if and only if condition, necessary and sufficient condition. I will come back. Okay. Okay. So next theorem I will talk about. So this is basically the submartingale. Then the idea is, so maybe you have seen it in my example previously, that I consider that summation over xi square minus n sigma square. Okay, if xi, which is a IIT with variance, it means expectation of xi is equal to 0, and variance is sigma square, then we are considering this yi, which is equal to the summation over I is equal to 1 to n whole square minus n sigma square. That is a martingale. That means we are subtracting something. Okay, so summation over square, it is a martingale. Then the whenever you consider the square, then that is a submartingale, is it not? And then you are subtracting something, it becomes a martingale. That is why we have seen this example. Then question is whether this is a general result or not. What I am trying to say is the following: if I have a submartingale, okay, then can I decompose it such that one component should be a martingale, and another component, if you look at that n sigma square I am having, so the property is basically it is increasing, okay, and 0 is equal to 0, a 0 is equal to 0 by definitions, and the other property will hold, because already we have talked about the predictable process. That means an is in fn and minus measurable. So in this case, since it is constant, means your example, then it is fine. So what I try to find out here, so-called the Doops decompositions, means I am giving you a submartingale. Can I decompose to a martingale the summations of martingale and the predictable process or not? Okay. This is a theorem. I am okay. Let's write down as a theorem that is called Doops decomposition. So what it says that any submartingale say xn can be written or expressed in a unique way as xn is equal to mn plus an, where my mn is a martingale, okay, n is predictable, increasing with a of 0 is equal to 0. Okay, so not only that, in the proof we will see that how my an looks like. Okay, it has a nice expression for that. Let us look at the proof. So basically we try to go like a trial and error method. Suppose I have a kind of this expressions and so on, and then looking at the final things, we will define accordingly and then we will prove it. Okay, so what we want? We want that xn is equal to mn plus an, Is it not? And expectation over Mn given say f of n minus 1, this is actually my m of n minus 1, and an is in belongs to f of n minus 1, an is increasing. Is it not? These are the things actually I want. So now that means what if I just try to start with here, so what I have expectation of xn given f of n minus 1. Okay, so then this part should be expectation of, because of this expression I have mn given f of n minus 1 plus expectation of an given f of n minus 1. Is it not? So now these things is nothing but m of n minus 1, because my mn should be a martingale. I'm not proving now, I'm just saying that okay, suppose this whole I want these things. So whatever I want final result, looking at this kind of trial and error method I am using here. Okay, and then so now an is a predictable I want. That means it is f of n minus 1 measurable. Hence this should be my an. Okay, so now this one again I know the expressions for m of n minus 1. This is x of n minus 1 minus a of n. So this is x of n minus 1 plus I have an minus a of n minus 1. So now x of n minus 1 is fn measurable. So these things actually I can write down in the form here that this is expectation over xn minus x of n minus 1 given f of n minus 1. Okay, this is actually is equal to an minus a n minus 1. Okay, so thus looking at these things we define exactly this one, that a of 0 is equal to 0, and for n greater equal to 1 I am defining an minus a n minus 1, which is same as exactly this part I can write down, or the previous one. Expectation over xn given f of n minus 1 minus x of n minus 1. And second thing I am defining that mn is equal to my xn minus an. Is it not? So now if I define these things, then actually we will see that okay, mn xn is equal to mn plus an. So now we have to show that an is increasing or not. Okay, and just you see that since xn is there, so an is increasing, and all these things are there. And also you can go to the back calculations to say that my mn is a martingale and so on. So I have defining in this form. Now you look at here, since my xn is a submartingale, I know that this part expectation of xn given f of n minus 1, this is greater than or equal to x of n minus 1, and hence this is basically greater or equal to 0. Okay, almost surely. That means my an is increasing. An minus n minus 1 greater equal to 0, that means an is increasing. And by definitions of an minus 1, and you see that it is a predictable. Okay, from these things I have, this is predictable, an is predictable. Okay, so now I have to check that whether it is a martingale or not. So for that case, expectation of mn given f of n minus 1, this is again expectation over xn minus an given f of n minus 1. And this one is what? This is expectation over xn given f of n minus 1 minus an. Okay, and this is, now look at the definitions I made it from here. This is nothing but x of n minus 1 minus a of n minus 1. Okay, just from the definition 1 for n greater equal to 1. So now this one again is by 2. Mn is equal to xn minus a of n, so x of n minus 1 minus a n minus 1, this is nothing but the m of n minus 1. This should be old, no, because we are just using the back calculations to find out. Sometimes no, this kind of argumentation is useful. So we have seen here that for any given submartingale, we can decompose to a martingale plus predictable process. Okay, not only that, it is increasing and with a0 is equal to 0. Let us try to prove the uniqueness. So that means what I try to show here, that okay, if you have two such of presentation, then we will show that they are unique. In particular, suppose there exists another martingale. Okay, so suppose there exists martingales yn, which is martingale, and predictable sequence say b of n, such that I have xn is equal to yn plus bn. So what is my claim? My claim should be that yn should be my mn almost surely, and bn should be an almost surely, because already I have one expression. So I'm saying that suppose I have another expression, another form, in this form. So then what I have to now look at, define my Zn. Okay, you define it. This is a mn minus yn, that is the naturally one can define it. Now it is a martingale, so it's a martingale. Okay, moreover, using that expressions mn minus zn, this is same as my an minus b of n, is it not? And hence, and an is fn minus 1 measurable, bn is b f of n minus 1 measurable, hence this is basically f of n minus 1 measurable, is it not? So thus I have two things. One thing is that if I look at Zn given f of n minus 1, this is actually z of n minus 1, because Zn is a martingale, this is the property, and expectation over Zn, which is same as yn mn minus yn, and this is same as an minus bn. So this is f of n minus 1 measurable, hence f of n minus 1, this is actually my z of n, is it not? This part I have the expectation of Zn, that means z of n minus 1 is equal to z of n for all n, that is the meaning, is it not? This implies Zn is equal to z of n minus 1, okay, for all n almost surely. Now look at what is my z of 0. This is nothing but my m0 minus y0, and this is same as your a0 minus b0, and this should be same as 0, because a0 is equal to 0, b0 is equal to 0, or in particular m0 is equal to also x0, y0 is equal to also x0, so it gives you 0. So this implies my the sequence, okay, Zn is equal to 0, and hence what we have, mn is equal to yn. So as long as you have mn is equal to yn, now from here mn minus yn is equal to same as an minus bn. So from this implies my a of n is equal to b of n almost surely. Okay, that means this expression is unique. Okay, so this expression is unique. Okay, so as an important application of decomposition is the following. I put as a corollary what it says that, so now I have my mn, which is a martingale, such that it is in L2, means expectation over mn square. This is finite for every n. Okay, that means whenever n is fixed, this is in L2. Okay, square integrable. So then what I am saying, then m square minus a, okay, is a martingale. Okay, then there exists a predictable such that, moreover, I have the expression that an minus a n minus 1, this should be same as expectation over mn minus 1 square given f of n minus 1 almost surely. Okay, not only that, furthermore, I have the following, that is called the Pythagoras theorem. So expectation of mn square I can write down as expectation over m0 square plus summation over I is equal to 1 to n expectation over mi minus 1 square. Okay, so this one is called the Pythagoras theorem. So what it says basically that if you have a square integrable martingale, then the Pythagoras theorem holds, and for that one needs to use so-called the Dup's decomposition theorem. Okay, let's see the proof. So now m means mn. Okay, m is equal to something like that, mn. So it's a martingale given to you. And what we have seen that if you have a convex function, okay, then such that phi of this mn square, if it is finite, means phi of mod of mn, whenever expectation of these things is finite, then phi of mn it will be a submartingale, is it not? Hence, since my that supreme over means that expectation of mn square is finite for every n, that means my mn square is a submartingale. Is it not? It is a submartingale. So now it is a submartingale, so I can use the decomposition. So what it says that I have that m square, I can write down my x plus a, where x it's a martingale and a is predictable increasing with a of 0 is equal to 0. Is it not? That is how the decomposition says. So now look at, so in other words, m square minus a is a martingale. That is the first part, says there exists a predictable increasing process a such that this holds. So m square minus a it's a martingale. So next we try to write down the things that this a I can have that a n minus 1 in the form whatever it is there. So now look at expectation over mn minus m over n minus 1 this square given f of n minus 1. Let us calculate this one. So what I can write down, this is expectation over mn square minus 2 times mn m of n minus 1 plus m over n minus 1 square given f of n minus 1. Is it not? So now this one actually I can write down, this is expectation over mn square given f of n minus 1 minus 2 times again m of n minus 1 I can take out because this is f of n minus 1 measurable, expectation over mn given f of n minus 1 and then plus again m of n minus 1 square, so I have m of n minus 1 square. Okay, so now this is actually I can directly write down expectation over mn square given f of n minus 1. So now m of n, this is a martingale, hence this is nothing but m of n minus 1 almost surely. So you have 2 times, that means I have minus of m n minus 1 square. Is it not? So this is same as my expectation over mn square minus m of n minus 1 square given f of n minus 1, because it is measurable, so I can take inside. Okay, so this part actually I can write down in a nice way, that is expectation over mn square minus an plus an minus n minus 1 and then minus mn minus 1 square minus an minus 1. Okay, given f of n minus 1 I can write down. So now this one is what? This mn square minus an, that is nothing but your xn. Okay, and mn square minus an is a martingale. So this part given fn is same as my this part. So this is nothing but expectation of n minus 1 given f of n minus 1. Is it not? So now an, this is predictable process, hence an is f of n minus 1 measurable. So this implies is f of n minus 1 measurable, hence this is nothing but my an minus a of n minus 1 almost surely. Okay, because my an is in f n minus 1 measurable. So what I have that an minus n minus 1, this is same as my expectation of mn minus mn square given f of n minus 1. So this proves the first part and the expression that an minus 1 can be written in this form. Okay. So let us look at the second part. So second part, what I have to have. So from here, from my previous one, what I have, if you take that expectation, then I have expectation of an minus a, or for any I minus 1 for I greater equal to 1. This is same as my expectation over mi minus 1 square. Is it not? Just like from here, what we have? We have expectation mn minus mn square given fn. So if you take that expectation, so this one I have. Okay. So now, what is my expectation over mn square? This part actually I can write down. This is m0 square and then plus summation over I is equal to 1 to n mi minus m of I minus 1. This one, is it not? And then take expectation. That's the telescopic sum. So now these things again I try to write down. This is expectation over m0 square plus summation over I is equal to 1 to n, because it's a finite sum, so I can take expectation inside, and this is expectation over, I can put it mi square minus ai plus ai minus 1, and then minus of mi minus 1 square minus ai minus 1. Is it not? So this is exactly same as expectation over m0 square, and then plus. Now see, mi square minus ai, this is a martingale, hence expectation of these things is same as my expectation of m of I minus 1 square minus ai minus 1. Is it not? Because for a martingale, what we know that expectation of xn is same as my expectation of n minus 1. So this got cancelled out. Whatever you end up with, summation over I is equal to 1 to n expectation over ai minus a of I minus 1. Okay, so whatever you have here, this one, so this is same as expectation over m0 square plus summation over I is equal to 1 to n. This one is nothing but expectation over mi minus m of I minus 1 square. Okay, that is actually we try to prove it. Okay, so what it says that for a square integrable martingale, we can write down the Pythagoras theorem. Okay, this is called the Pythagoras theorem. Okay. Okay. Next, we try to give some applications, in particular about the independent random variable. So I try to put as a theorem form. You will see that application of Doops martingale again. Sorry, the Doops decompositions and so on. What it says that, so I have a sequence of random variable xn. Okay, they are independent. RBs means random variables. So such that expectation of xn is equal to 0, such that for all n, and I put sigma n square, which is my variance of xn. Okay, they are finite. Means for each n, this is finite. So then I have the following result. So if my summation over n is equal to 1 to infinity of sigma n square is finite, then summation over n is equal to 1 to infinity xn converges almost surely. So here actually we try to know that when independent sequence of random variable, the series converges almost surely or no. So here actually I say that one part, that if the summation over n is equal to 1 to infinity sigma n square is finite, then summation over n equal to 1 to infinity xn, it converges almost surely. Okay, so here maybe there are some probabilistic approach to prove these things, but here we try to use the martingale concept to prove this theorem. So you can think of as a various applications of martingale things, which is not related here, but still you can apply here, because here you don't see any martingale and so on, is it not? But still actually we can do it. Let's see how to do it. And what about the converse? So whether that summation by n equal to 1 into xn converges almost surely implies whether this thing is finite or not. Okay, but answer is no, but under certain assumptions the converse is true. So what is that? So suppose in addition that xn is bounded, that is there exists my k positive such that my xn of omega, this is less than k for all, means almost surely and for all n, then the converse hold, then summation over xn converges almost surely implies that summation over n is equal to 1 to infinity sigma n square is finite. Okay, so I will prove only the first part, means part A, and you try to prove yourself by 2, and if B, if there is some problem, then I'll do it. Let's look at the proof. It's a very nice thing. So you will see that how one can use this groups decompositions and so on to prove these things. Okay. So now define f0, which is my phi and omega. This is the trivial sigma algebra, and fn, which is sigma generated by x1, x2, and x of n. And I put m0 is equal to 0, mn is equal to summation over I is equal to 1 to n of xi. Okay, I put a0 is equal to 0 and a of n, which is summation over I is equal to 1 to n sigma I square. Okay, and n0, why I am defining that you will see, just a minute, you will see n0 is equal to 0 and nn, which is something like that mn square minus a of n. Okay, that is for n greater equal to 1, this is for n greater equal to 1. So already we have seen that if you consider, see, IIT sequence, actually we are using independence property, but I need expectation of xi is equal to 0. Okay, so that it will be a martingale. Already we have proved the theorem. So Mn, this is a martingale because expectation of xi is equal to 0, it is given to you. Okay, you don't need IID, but at least only with respect to expectation, if it is given to you and if it is independent, then actually Mn is a martingale. So moreover, what is your expectation over Mn minus m of n minus 1 square? This is nothing but expectation of, this is x of n square, and this is nothing but the variance, and hence sigma n square. Okay, and this is finite, so expectation of xn is finite. Okay, is it not? And hence actually you will see that expectation over mn square, this is finite for every n. Okay, this is for every n, this one is finite. Hence by the Pythagoras, because now mn is a square integrable martingale, hence I can write down expectation over mn square. So by Pythagoras, I can write down this is expectation of m0 square, which is 0, and then summation over I is equal to 1 to n expectation over mi minus mi minus 1, that square, which is actually is equal to expectation of xi square, and which is sigma square. This is summation over I is equal to 1 to n sigma square, okay, which is actually is equal to my a of n. So now in your condition A, so if A holds, then what I have, that this one summation over I is equal to 1 to infinity sigma square, this is finite, okay. So that means I can take supreme over n expectation mn square, this is finite, okay. So this implies supreme over n expectation over mn square, this is finite, that is my m is bounded in L2, and hence actually I can write down this implies supreme over n expectation over mn plus, this is finite. That is trivially true, no, because this is bounded in L2, hence it is in L1, because if it is in LP for P, and then it should be always LQ whenever Q is less than P, okay. So this part I have. So now Mn is a martingale, hence it is a submartingale, and this property holds. So my martingale convergence theorem, what it says, that limit n goes to infinity Mn, this exists almost surely, is it not? So that means what? If my Mn exists almost surely, and what is by your definition Mn? This is I is equal to 1 to n xi, and this converges almost surely. So in other words, summation over I is equal to 1 to infinity xi converges almost surely, okay. So they say that I'm not going to prove the part B, you try to yourself, and if there is some problem then I'll do it, okay. So you see the nice application of martingale theory to prove this infinite sum of a independent sequence, whether it converges or not, okay. This is kind of one applications, okay. So next we talk about so-called the convergence in LP, okay. So for P greater than 1, okay. So what we know, you remember maybe the Markov inequality, what it says that if you have a, say, non-negative random variable, then probability of x is greater than, say, epsilon or alpha, that should be equal to 1 by alpha to the power p expectation of mod x to the power p if x is in LP, is it not? So we are try to use this kind of argumentations, but we can find out the better if it is a martingale or submartingale. So for that I need one inequality that is called the Doops submartingale inequality. So I put as a theorem Doops inequality or submartingale inequality, generally called Doops inequality or maximal inequality, something is called, okay. So what it says, that my M, which is my Mn, it's a non-negative submartingale, okay. Then for NEC, what I have, that probability of, now supreme over k is less equal to n over mk greater than or equal to c, this part I have less than or equal to 1 by c times expectation mn over supreme over k is less equal to n, mk greater equal to c. Okay, that means integral over in that set mn dp, which is less equal to 1 by c expectation over mn. Okay, so basically you see that for the random, for the discrete sequence, what you know that for each mn greater equal to c, and then you have this part. But that is why I say that for some martingale case it gives you more, it's a more stronger result, because what is the superior k less equal to n, mk greater equal to c, it gives the same thing else. Okay, so in that sense it is a stronger result. So this one is nothing but basically this is same as 1 by c integral over supreme over k is less equal to n, mk greater equal to c. In this shape you have mn dp. Okay, or you can think of this is the characteristic function, mn times characteristic function over this part, expectation of that, exactly same. Okay, so let us try to prove it. So proof is very nice. What it says that now I define this set, this one. Okay, all those omega k is less equal to n such that my mk is greater than equal to c. So idea is I can write down my this set A as a disjoint union of my sets fk such that it has certain properties. Basically they are disjoint. F can be written as union over k is equal to 0 to n of fk. How I will do these things? Because f0 is attends, which is my m0 is greater than or equal to c, and then either it will be in an end point. That means my f of k, which is intersection over I is equal to 0 to k minus 1, mi is less than c, intersection mk is greater or equal to c. Okay, for k is positive. In this way, actually, you see that this f supreme over k less equal to n, m greater equal to c is I am having in these things. Okay. So now we see that each fk, because of this mk is a submartingale, each fk is f of k measurable. Okay. So each fk is f of k measurable. And not only that, by our construction, fk's are disjoint. So since they are disjoint, the good thing is that since f I have these things, so if you look at the indicator functions corresponding to that, then I have the summations of the indicator function. So indicator over f, this is same as my summation over k is equal to 0 to n indicator of my fk. Okay, and hence what I can have, since my m, this is a submartingale, so then what I can have, and fk is f of k measurable, so I can have expectation over mn, and then this set fk, this is nothing but what, this is integral over fk mn dp. Okay, is it not? So look at the definition of conditional expectation. So this should be less than equal to expectation over mk over this set fk, is it not? The submartingale inequality, because m is a submartingale, so I have these things, and this part is less than equal to, because in hk fk what I have, everything is bounded by c, so this is actually expectation over c over fk, and this is nothing but c times probability over fk, is it not? Because on fk, this is my fk. Okay, so I have mi, this is less than c, intersection I have, so this is less than c, I have my c times over fk. So what I have now, if you take that summation over k is equal to 0 to n. This implies C times summation over k is equal to 0 to n probability over f of k. This is less than equal to summation over k is equal to 0 to n expectation of mn over the set fk. Okay, that means I can look at the characteristic function over fk. So now this part, okay, is nothing but the c of f, because f is the union over fk. Okay, so this implies c over probability over f, because I am using this property. This is less than equal to expectation over mn over f, which is less than equal to expectation over f mn over a. Okay, because mn is my positive, so this is integral over f, and then I have integral over whole set omega. So this is expectation over mn. This is exactly we want to prove it. If you just look at in this definition, the theorem, exactly this one actually we want to have. Okay, so this is called the Dup's submartingale inequality or Dup's inequality. So this is for non-negative submartingale, and then generally if I give you as a martingale, okay, then I can consider the modulus of that will gives you a submartingale, and also it is a non-negative. Okay, so this is other things I can think of as a corollary. If my Mn is a martingale, then for every C positive, what I can write down, that C times probability over supreme over 0 less equal to k less equal to n mod of mk is greater than or equal to, say, C. Okay, this is less than or equal to expectation over mn. Is it not? Because I can consider mn is a martingale, so mod of mn it should be submartingale. Is it not? By Jensen's inequality, and then you have this part. Okay, so here what I consider that, okay, I have a submartingale, so that this expectation is thing there. So what happens if we have a higher moment? Whether can we have a similar kind of inequality or not? Okay, so this is given by so-called the Dup's LP inequality, another theorem. I am not going to prove it, but proof is simple, so you can check yourself. This is called Dup's LP inequality. Okay, what it says that if M is a martingale or non-negative submartingale and P is strictly greater than 1. See, for a martingale or submartingale, what do you know that it is in L1? No, for every n it is L1. No, that is the conditions to define a martingale or submartingale or supermartingale. But what it says that it is in LP. So then I have expectation over supremum over k is less equal to n mk to the power p. If you look at, then this should be less than or equal to p by p minus 1 to the power p expectation over mn to the power p, provided that m is bounded in LP. That means this should make sense. Okay, m is bounded in LP means basically superior over n expectation over mn to the power p. This is final. That is the meaning that m is bounded in LP. Okay, so this part actually it is required. So basically here is nothing. You try to look at what is the meaning of these things. Okay, and then use called the Fubini's theorem, means you can interchange the two integrations and so on, and then one can find out. So I'm not going into prove this Dup's LP inequality, but I just stating this result and I'll use this part. Okay, So previous one gives you only for a non-negative submartingale. Then I have this inequality which is a stronger result compared to your Markov inequality, whatever you already means, whatever already you know that part. This is gives you more stronger result. So idea is here using all these things we try to show when if I give you say martingale lies in say LP, bounded in LP, can I say that my xn converges to some random variable x in LP? Okay, that is why I say that okay LP convergence. So as a consequence of these two inequality, I have the following theorem. So if xn is a martingale, this is a martingale bounded in LP for p greater than 1, then xn converges to x infinity almost surely and in LP where my x infinity is nothing but the lim sub over n xn. Okay, how to prove it? So by martingale, see xn is bounded in LP, hence I can think of no supreme over n xn plus expectation of xn plus that is finite. So bounded in LP for p greater than 1 implies that supreme over n expectation over xn plus is finite. Okay. Hence by martingale convergence theorem, what I can say, so there exists x infinity, not only the x infinity exactly lim sup over n over xn such that my xn converges to x infinity almost surely as n goes to infinity. The martingale convergence theorem only gives the almost sure convergence. Here we try to show that indeed it converges in LP. How to show this part? So like in Doobb's LP inequality, what it gives you, so by Doobb's LP inequality, what I have that expectation over supreme over say 0 less equal to m less equal to n mod of xn to the power p, this is less than equal to p by p minus 1 to the power p expectation over xn to the power p, is it not? And you observe this one, that supreme over 0 less equal to m less equal to n over xn, this is increasing and it converges to supreme over m is positive of mod of xn, is it not? So now I have this is increasing, it converges to these things almost surely, and this part in LP it is bounded by some quantity which is in L1, because my xn it is uniformly bounded in LP, hence this the pth norm is uniformly bounded in L1. So that's why I can use basically monotone convergence theorem or the dominated convergence theorem, whatever you want. So I have that by monotone convergence theorem, I have that expectation over supreme over m is positive xm to the power p, this should be less than or equal to the limit m goes to infinity. That means this part I have which is p by p minus 1 to the power p expectation over or suprema over n xn to the power p. So this one is finite, is it not? So that means what? This is a non-negative quantity, okay, and I have this part, expectation of these things is finite. This implies supreme over m is greater equal to 0, xm to the power p, this is in LP. That is the meaning of that part. No, this is in LP. So now what I have to show that? I have to show that xn minus x infinity to the power p, that is converges to 0 in converges to 0, expectation of that. So now again you observe that xn minus x infinity, okay, so maybe note that these things actually I can write 2 times supremum over m is positive of my xn, because x infinity, which is nothing but the lim sup of xn, so I have my this part, okay, and hence if you consider the pth norm and then pth norm is there. So now this thing is in LP, this part already we have seen it. Sorry, since I put that to the power p, this is L1. I made a mistake. Whenever I put as a p, then it should be L1. If we don't put it p, then it should be LP. So whatever you want. So maybe I put p and then this should be L1. So this is now L1 of omega. Okay. So that means xn minus x infinity p is in L1 of omega. Okay. So hence by dominant convergence theorem, I can say that my xn, this converges to x infinity in LP of omega. Okay, so here I have convergence in LP. What it says that if you have a martingale, okay, which is bounded in LP, then there exists a random variable x, which is also in LP, such that xn converges to x in LP for p greater than 1. Okay, so martingale convergence theorem only gives you almost sure convergence, not any LP convergence. But using my Dup's LP inequality for p greater than 1, where you can also use this Dup's martingale inequality, from there we say more, okay, that if my xp is in L1, then, or in particular if x is bounded in LP, then I can have convergence in LP. Okay. So now we'll come back again in martingale convergence theorem. As I said that I want to know when it will converges in L1. Okay. So for that I need some notions for that. In particular, maybe you are familiar with, it's called uniform integrability condition or uniform integrability condition. Okay. So I put as a definitions uniform integrable. So what it says that I have a collection of random variables, say xi, I is from index set, this I. Okay, it may be whole n, the set of natural number, or maybe others. Okay, it's a family of random variable. So say that is uniformly integrable. In short, I put as a UI, uniformly integrable, if I can say that whenever limit m goes to infinity, supreme over I is in I, integral over xi is greater than m, this set xi dp is actually 0. That means what it says that the tail part of my xi, I can uniformly control that part. that is uniformly integrable. Okay, the tail part actually I can find a big n such that integral over xi is greater than m for all I, not only for say x1 is greater than m, x2 is greater than m, all over the I for all sets. That means the tail part uniformly I can put really less than the integral over on that tail part, it is really less than epsilon. So what is this meaning, limit of this thing? This means given any epsilon is positive, there exists a m such that integral over mod of xi greater than m xi dp, this is less than epsilon, is it not, for all I is in my index set I. Means the tail part you can uniformly control, or you can uniformly think of really less. Okay, then it is called uniformly integrable. So as a consequence of this definition of uniform integrable family, it is bounded in L1. So as a remark I say, I think you have done it in your major theory course, this one, but still I need to just recall it. If xi I is in say integrable family ui, then it is bounded in L1. What do you mean for that? So for suppose for epsilon say greater than 1, I can find a k is positive such that integral over xi is greater than k of xi, okay, dp. This is less than 1 for all say I is in my index set I. I took epsilon is equal to 1, then I had. So what I have to show? I have to show that expectation of mod xi, okay, this should be, or supreme over I exponent, this is less than or equal to some constant, okay, uniformly. So these things actually I can write down in a two set, which is xi is less than or equal to k over mod xi dp plus integral over, because I am just decomposing omega into a two disjoint sets where xi is greater than k over xi over dp, is it not? So now you see on this part, this is less than or equal to for this part I have less than 1, is it not? And from here on this set xi is less than or equal to k, so I can have this is k times probability over xi is less than or equal to k, is it not? xi less equal to k, I have this integral over this is the probability, and plus I have this set integral over xi is greater than k xi dp. Okay, so now these things probability less than or equal to 1, so I have k plus this one is by definitions it is 1, means using my this part. So that means expectation of mod of xi less than or equal to k plus 1. Okay, so it is bounded in those things. But what about the converse? Means can I say that if a sequence xn, if it is uniformly means bounded in L1, then whether it is uniformly integrable or not? Answer is no. So I am saying that the converse is not, or in particular the uniform integrability, or sorry, the boundedness in L1 does not imply in general ui. Okay, ui implies bounded in L1, that is actually we have seen it, but bounded in L1 it does not imply ui. So let's see, for example you consider xn, I am considering the sequence, this is n characteristic function over 0 1 by n. Okay, and take your omega is equal to say 0, 1, P is the Lebesgue measure, and F is the Lebesgue sigma algebra on 0, 1. Okay, the usual thing actually you consider. So now, what is your expectation over xn in this case? This is basically n times and then 1 by n integral over that part. Okay, so this is nothing but the 1. So expectation xn is equal to 1 for all n. Hence, this implies it is bounded in L1 of omega, is it not? But whether it is uniformly integrable or not, question is no, because so for n is greater than k, for all k fixed, integral over xn is greater than k. On this set, if you look at my xn dp, this is actually is equal to 1 because of my this concept. So that means what I say that the limit m goes to infinity, integral over mod of xn greater than k xn dp is equal to 0. That is not possible. Okay. So for any k, if you give me, I can choose n bigger enough such that this happen. So it is not uniformly integrable. This implies not ui. Okay. So the general concept is that uniform integrability implies boundedness in L1, but boundedness in L1 does not imply uniform integrability. Okay. So I try to give you one thing, that if it is uniformly bounded, not in L1, just uniformly bounded, then it is always uniformly integrable. Okay, the sufficient condition I am saying. And another is I am going to say that if it is bounded in LP for P greater than 1, then it is uniformly integrable. So the sufficient condition actually I am thinking of as a theorem. So xi, this is bounded in LP for P is strictly greater than 1, because for P is equal to 1 we have already seen that one example. Okay, then the family is uniformly integrable family. How to prove it, and then I will stop it. So proof is simple. So now epsilon is positive, okay, and let q which is greater than 1 such that 1 by p plus 1 by q is equal to 1. No? The associated exponential of that, this I can write down. Okay, there exists a q greater than 1 such that because p is greater than 1, so I can have 1 by p plus 1 by q is equal to 1. And you consider m which is my supremum over j, expectation over xj to the power p. This one is finite because it is given to you that the family is uniformly bounded in LP. So I think you know the Holder's inequality from maybe your major theory course. What it says that integral over xj greater than k, we want to write down, no, this is xj dp. So these things is nothing but expectation of xj, and then I can think of this is characteristic function over mod xj greater than k. Is it not? So now I have two. So integral, this is something like the integral over fg less than equal to fp norm g q norm. No, where 1 by p plus 1 by q is equal to 1. This one actually you have seen it there. The Holder's inequality. Exactly same thing else. Now f is my this one. Integral is nothing but the expectation, and g is my this one. So if you just look at by Holder, what I have, this should be expectation over xj to the power p, and then to the power 1 by p, and then this is to the power q, but this is same as expectation is the probability over xj is greater than k, this is to the power 1 by q. Okay, so now these things actually I can write down again, expectation over xj to the power p whole to the power 1 by p, and then this one, now probability over mod of xj less than k, I can think of this is k to the power p expectation over xj to the power p, and then whole to the power 1 by q by Markov inequality. This one is coming because of Markov inequality. Already you know these things. So now this is less than or equal to, I can take the supremum of that. So I have m times, because 1 by p plus 1 by q is equal to 1. So I have expectation of xj to the power p, hence I can take supremum over j, this is less than or equal to n. And then I have k to the power, this is q minus p. Okay, this is minus p by q. So these things actually I can put epsilon, okay, when I can choose my k, this should be greater than m by epsilon time p by q. Okay, so I can choose this k so such that this is less than epsilon. So this shows that my family xi is uniformly integrable. Okay, so if it is in LP, then it is always uniformly integrable. Okay, I will stop now.